expand this out, you actually simply get a linear relationship, right? This is just, because if you think about it, when you multiply these three weight matrices together, you just get another weight matrix. And then all of this is just some scalar bias. So you're doing all this computation, but really it's equivalent to just having one layer. So you really haven't gained anything. So where the real magic comes in is when you actually start putting activation functions on those outputs, then you're basically warping your previously linear relationship, you're warping it into some nonlinear space, which basically, and this is kind of the magic that allows you to, or that allows neural networks to, classify in interesting ways or regress in interesting and nonlinear ways. So some of the functions that you choose, so obviously the function that you choose for f is really important. And some of the most typical ones that you'll see are sigmoid, tanh, ReLU, and then leaky ReLU. This is a bit more modern. But basically, the idea behind all of these is that they're really easily differentiable. And we'll talk about why in the next slide. But, in terms of talking about these functions, you can kind of see that, yes, ReLU and leaky ReLU, they're kind of linear. They are kind of sending the input immediately to the output. But for something like this, you can see that there's a really sharp nonlinear representation. There's a nonlinear boundary between your input and your output. So that's kind of where that representation power comes in. So why do we want these to be differentiable? Well, it's actually because the way that we train neural networks. So if you remember from the last lecture, we talked about something called gradient descent. And gradient descent is where you take the gradient of your loss function. So remember, we also had loss functions introduced in the last lecture. So you take the gradient of your loss function, and in a parametric model, you take the gradient with respect to the parameters, or the weights in this case. And then basically, you use this gradient to update those parameter weights. And that's kind of gradient descent. That's the very vanilla algorithm that we saw before. So what that means in a neural network sense is you now have to take the gradient of your neural network. And so, although there's this kind of interesting computation structure, because the functions we're choosing here, they all have well-known, easy to compute gradients, we can actually just do this gradient descent operation on neural networks very easily. And the way that we do this, the way that we train is we really make heavy use of the chain rule. So, the overall algorithm is, so if you remember in gradient descent or in mini-batch gradient descent, you sample some subset of your data set, which could be huge. So you sample some amount of data, you propagate that through your network in order to obtain a value for your loss, and then you take the gradient of this loss, or you use the kind of pre-computed gradient of this loss with the value that you obtained for the loss, and then you back propagate that error all the way through the network. So that's a lot of words, but really what's going on internally is, so you're taking, if you remember, the way that a neural network is structured, the next layer's output is, it itself takes as input the output of the previous layer. So, when you have multiple layers, you're actually composing multiple functions together. So if you remember, that has sometimes this notation here. It's kind of f of g, f composed of g. So all that we're doing, when we're backpropagating through, when we're taking the gradient of the network through these composed layers, we're just applying the chain rule in order to, find out what the analytical form of the gradient is at lower layers. So this is what it looks like here. And basically, we use this information, and then we can very easily and very computationally easily calculate the gradient of the loss with respect to each of the weights in the network. So remember, we don't just have, this isn't just like your typical parametric model where you only have one set of weights. Here we have a weight here, here, and here. So we actually need to take the gradient of the loss with respect to this weight, and this weight, and this weight. And then we have to update that as well. So that's why we need to take use of this, this chain rule in order to get the value of the gradient at each of those weights. And then we update those parameters using that same update rule that we saw last time. This is, that exact same gradient descent algorithm. cool thing, like I said, it's very computationally easy to do this. Why is that so easy to do? Well, when you end up computing the gradients and you kind of write out the chain rule, parts of the chain rule actually require you to have the values from the forward computation. So the great thing is when you run a network like this, you can actually save the intermediate outputs. So you kind of save the values that it output here. You save the values that it output here, and you save the value that it output here, which is just the output anyways. And then when it's time to back propagate, you can use those intermediate values, and you don't have to recompute anything. So it's actually very fast to do this, which is great because we have to train a lot of times. So to step back and put some pictures to these words, when you're training, you remember that we have a massive data set. Could be millions of images or whatever, or millions of data points in this case. You remember that we have a massive data set. Could be millions of images or whatever, or millions of data points in this case. So we subsample, we step, we forward propagate. So this is kind of going forward through the model to the output. We obtain a final value, which we then use to calculate our loss. And then this loss, we back propagate through the network in order to update the weights. And then we repeat this ad nauseum until you have a really good loss value. In inference time, so when you're done all of this training, you obtain a trained model. So remember, when you have a parametric model, you can now ignore all of that input data, and you can just use the learned parameters to compute values online. So what we do is we take this trained network, and then we have some intermediate number of test data points that we want to run. And then all we're doing is we're doing forward propagation and obtaining our output y. And then this is what we send that's our result. That's the result of our model, and then use that how you will. So if you remember before, we talked about something called overfitting. And I think I drew I made some funny joke about some deciquintic polynomial, which kind of overfits to all of the points in your data set because it's a really powerful model. So neural networks, if you can imagine, with all of this multi-layered, nonlinear computation, they are also really, really powerful. There's actually a theory from some old paper that you'll never read, but just know that this exists. There's a theory that says, even if you only have one layer, so just a single layer neural network, if it's wide enough, which means if you have enough hidden units or neurons in that hidden layer, you can approximate any function in the entire world. This is called the universal approximation theorem. And this is basically what gives neural networks the credence that they are as strong as we claim they are. So they can really model anything. The problem with this is that they can also model your training data really, really, really well. And then you overfit really easily. So how can we combat overfitting? So if you remember before, we looked at methods of regularization. So the same methods of regularization apply to neural networks, just to say. So if you remember, we added an L2 loss on the weights. So this is basically in a parametric function. If we had something like an L2 loss, which basically looks like this, and this is just the loss for one training point. We basically take our output, yi, and I'll mark it with a hat for, this is the predicted output. And we compare it with the ground truth, y. So we take their difference and square it, and this is, in like a regression problem, for example. So, you can have a loss, so this is the L2 loss for regression, but if we wanted to regularize whatever function produced this y, then we would add something like, this L2 regularization penalty in order to keep the weights small. And in neural networks, the exact same thing applies. You can add the exact same L2 or even L1 regularization penalty to your loss function to encourage the weights to be small. This works. Something else that works, and actually there's two methods here. Another very popular method, and this was introduced, 2012 or something like that, maybe 2013, 14, is something called dropout. So in dropout, so if you remember in our typical neural network architecture,
we have these multiple layers and they're going to the output. What you can do is during training time, you can actually randomly zero out some of these internal neuron outputs. So this seems a little bit, unintuitive because you're really hampering the performance of your network by just randomly zeroing out some of the neurons. The reason we do this is to prevent neural networks, or specifically we're trying to prevent specific neurons in the neural network from becoming too specialized. The reason I say this is because if you have a too specialized of a neuron, what it's really doing is it's just trying to memorize some part of the input data set. So it's not really helping you when you want to use this neural network in the real world. It's only helping you for the training data set, which isn't really useful. We don't want to encourage that behavior. So for example, if we wanted to try and classify what a cat is from an image, if you have some neurons which kind of learn, oh, okay, it has an ear, it has a tail, it's furry, it has claws, and then maybe it has a bad look on its face, then you might, the good thing is when you zero out some of these activation values, it forces your network to be redundant, which means it can still work correctly even if it only has 2 or 3 of those same neurons firing. So that's one method, that's a very popular method. The other one, which is extremely popular, I think everything in the world, every model in the world uses this, this little trick, is that you can actually transform your input data in some way. So this is, again, because we want to focus on image detection and image processing, we're going to look at examples with images. So in the image, in the computer vision world, the way that you can transform your input data to kind of artificially give you a larger set of data to train on is, if this is the actual image in the data set, you can generate like 3, 4, 5 different versions of this by, scaling it or stretching it, rotating, adding noise, dropping some of the pixels. I mean, I think when I had, I was working with, some computer vision models, some deep convolutional networks some 2 years ago, and if I had a data set of 50,000 images, you could upscale that to like 1.2 million images completely for free just by doing this kind of stuff. And this is excellent because it forces your neural network to learn a robust representation of the data you're putting in. It forces your neurons to not just pay super close attention to some special things. They're trying to, you're trying to force the neurons to have a general representation. So this was a lot of talking about neural networks and just about the math. So let's actually look at what they look like when they're training. And this is a really nice, oh, Mark, you don't have internet. Let's fix that. Where's the mouse? I should just connect to Stanford, right?
Yeah.
Oh, you just turned it off?
Yeah.
It's all good.
Just connect to Stanford, not Stanford Vita.
I know. Now I'll see if I can bring this over, to this side. Are we connected yet? Oh, come on. So what we're gonna look at here is a visualizer, or it's a visualization made by Google as part of their TensorFlow project, which I think you guys are now quite familiar with. So this is basically trying to show you how the training process looks like in a neural network, how the output changes as you see more data. It's really cool too, so eventually this is why I really want to show it, because I think it really gives a good intuition on why they're so powerful and how they work.
Just wait.
I know, I'm waiting. Hey, excellent. Oops, do I have to? This is a lie. Amazing. Finally. Okay, so this visualizer, what it shows you is, okay, so there's a lot of information here. Let's just break it down a little bit. So on the top row here, you can see, okay, this is the controls for, do you want to start the simulation or stop it? So cool, we know this. Epoch, this number counts how many times has your neural network seen the full data set. What this means is, remember how I said we're subsampling the initial data set in order to train on smaller batches and then use those to update? So if you have a data set of size 10,000 and then you're training on a subset of 100, how many iterations does it take until you see the full 10,000? Well, it takes 100. So basically after 100 steps, you will have gone through one epoch, which is one step over your entire data set. So that's what this counter is going to show us. Here we have some SGD parameter, some gradient descent parameter. This is how your learning rate, this is how fast you're doing your updates to your weights. So remember our activation, which is really important. So it's showing us here which activation it's using. Right here it says TANH, in case you guys can't see. We're not going to put any regularization. There's options to put regularization. And then here we're focusing on a classification problem. So you can see here, this is the data set that we're trying to classify. So you can see here in the middle, there's like a group of blue dots, which we want to separate from this ring of orange dots. So before I even press play or do anything, I really want to make you guys realize this is impossible to solve with a linear model. Why? Because a circle, which is the boundary that we're looking for, it's clearly a nonlinear relation that you were trying to learn. So I'm going to tell you right now, there's no way to do this with a linear model. Absolutely no way. So that's why with neural networks, we can actually learn this. So what you see here, so boom, already, after what, 200 epochs, you can see the neural network has already come up with a really strong decision boundary here between orange and blue. And what it's showing over here, so this is the actual visualization of the internals of the neural network. So you can see here, these are the inputs, specifically their features. So you can see what kinds of features they're trying to feed in. Here it's like orange on one side, blue on the other, blue on the top, orange on the bottom, and then you can actually add some more complicated features. Then you can see this is the first hidden layer, and the thickness of these lines is signifying the value of the weights. So you can see here there's some high weight values over here, and then there's some smaller ones over here. So here's our first hidden layer. Here's our second hidden layer, and then then they're actually hiding this. They're crafty, but they're actually hiding this. But there is a final output layer, which is then giving you just the classification result. Because otherwise, how do you get a classification result from 2 neurons? So the cool thing is about this is we can actually change some things. Let's say we wanted a crazy neural network, 4, 5, oh my God. How many? Okay, 6, that's ridiculous. Yeah, that's way too much. But if we do 6 hidden layers, 8 neurons, let's go wild. 8 neurons. So what am I trying to do here? What will happen if I give a ridiculously powerful model like this? Someone yell out the word. It will overfit. It will 100% overfit. It's going to look ridiculous, I hope. Otherwise, then I just don't look like, I look like I don't know what I'm doing. All right, so we're going to try doing this pretty hardcore model. Let's give a different data set, because I want to, sorry. What I want to also do is I want to show the test data. Okay, so do you see, this is the training data set. Do you see that there's dots with white lines around them? There's now some dots with black lines around them. This is the hidden test data. This is like the data that we really want to perform well on. All right, so let's use this ridiculous model and learn some, but these, these are all really easy things to learn. Sorry. What I want to do is I want to add, there we go. I want to add noise. So now take a look at this. So do you see how there's now, it's not so easy, right? There's some values of orange where the other blue things are. And the longer I run this model, so this is also super important to show you guys, but it's kind of hard to show here. I hope I can zoom in over here. Excellent, excellent. Do you guys see this curve here? Let me make it even bigger. This is important. So remember, we have this ridiculously powerful model. So there's two losses that are being plotted here. The first, in the, I don't know why they picked gray and black, but in the gray, in the less black color, this is the training loss. This is how well your model is fitting the training data set. So as you can see, it's amazing, right? It goes straight down to 0.111. Okay, so it's pretty good. Of course, it's gonna miss these, but something that's really interesting that happens is when you look at the test loss, it drops down, as we'd expect, it hits a minimum point, but then it rises again. So this flat part, it's not just flat at that minimum value, it's actually rising again. Why is that? Because now the network has said, all right, cool, I've learned the gist of the data, but now I'm going really hardcore and I'm gonna really try and extend my, I mean, I guess it doesn't show here, but it's really trying to extend and perfectly classify every single training point. But that actually costs you in the test data set. So that actually makes the loss for the other data set increase. And this is a classic example of overfitting. This is actually how you can tell if you're overfitting. Anyway, so that was a lot on that. We will have more visualizations, don't you worry. So, wow, that makes everything, oh my goodness, that makes everything slow. Okay, cool, so we're back here. So, from neural networks, we're now going to go on to the more image-specific architecture called convolutional neural networks. So let's talk about what that means. So if we wanted to, if we have an image, and we have, you know, our favorite tool, the multi-layer perceptron, or the, you know, the typical neural network, what we can do is we can actually just take that neural network and then in a sliding window fashion, just run it over groups of pixels here in the input image. I mean, and this would work. You'll get a lot of, you know, classification values for different groups of pixels, but the problem is that's actually throwing away a lot of information. And the reason I say that is because images, and really the visual world all around us, has something called spatial locality. What that means is this one pixel here, somewhere in the middle here, is actually going to be pretty similar to the, you know, 10 or 15 pixels around it. I mean, unless you have a really sharp gradient in your image, you know, this white pixel here, you know, on a cat, it's not going to now sharply change color like random noise. There's going to be a smooth gradient into this orange, you know, part here, or maybe this black part up here. So, you know, there's kind of, within one area of an image, you get a lot of information about the surrounding area as well. So when we use this sliding window information, we're kind of throwing that away. And not even that, but we're throwing it away because one neuron, like some of these input neurons here, they don't tell the other input neurons about this information. And that's kind of where you're losing a lot. So this is what we just learned now. And the other really predominant method of working with images is using something called a convolutional neural network. And that's kind of visualized over here. So the core idea of a convolutional neural network is that you can take, you know, this, if you have this spatial locality, which images do, you can implement weight sharing, which means you can do something like scanning across the image, but use the same weights, rather than just having a neural network for, you know, every 10 pixels, and then you're kind of completely, you have a huge amount of parameters, and you're completely ignoring this spatial locality. So, you know, to talk about convolutional networks, usually they're architected like so. From an input image, so here you're actually giving it an image, you're not just stretching this image into a single column and doing, you know, doing some linear, you know, some linear operations on it. From an input image, you usually feed this through some convolutional layers. We'll talk about what that looks like. From these convolutional layers, you then usually, you know, you still have the nonlinearities. We're still running, we're still using that activation functions, those Fs. And then usually you have some pooling layers. We'll talk about what those mean. And then after all of this, we then have our, you know, our multi-layer perceptron at the very end, which takes this interesting representation and then actually gives us our classification. So, you know, what we learned was not for nothing. They are still being used, and usually it's right at the end. So let's actually talk about each of these layers, and specifically, conv and pool. These are the two kind of interesting parts of a convolutional neural network. All right, so what a convolutional layer does. So for example, your input image might be 32 wide by 32 tall, and then if it's a color image, it's going to have 3 channels for RGB. So if you have an input image, and then usually you have a convolutional filter. So again, don't worry, we'll go into more details, but basically you have something like a 5 by 5, and then if it's color, by 3 filter. So when I say filter, you can actually think of the word weights, because what's going to happen is we are going to convolve, we're going to use the convolution operation to slide this filter over this input image, and then we're going to get an output at each location. And okay, so it's exactly this operation. And so then this output gives you, so remember before when we had after the activation function, we get an activation value, just like a single scalar. It's exactly the same here. You're going to get an activation value for every point that you scan over the input image, and then this gives you something called an activation map. So rather than an activation value, you have a lot of activation values, so you get an activation map. Now, how do you actually obtain these activation values? So when you're sliding this filter over the input image, the mathematical operation that you're doing is exactly what we've seen before. What you're doing is basically this filter, which I said you should think about as weights. You're taking this weight, well in this case it's a weight tensor, but you're basically stretching out this weight tensor into a single column or row. You're stretching out the pixels that are contained within the filter area from the input image. You're stretching those out into a column, and then you perform the thing that we have been performing all this time. You perform the dot product between those two, and then you add a biasing value. So you're doing this Wx plus b all over the input image. So you're doing this sliding window all over the input image, but the key here is that you're using the same weights for all of those. So this is how we exploit the spatial locality that images have. So then, like I said, when we do this, when we slide all over the spatial locations and we get this output value, we then obtain an activation map. And the size of the map depends on the size of your image, the size of your filter, and some parameters about how you move across the image. We'll talk about this, don't worry about it. Now, the cool thing is you don't just have to have one filter. So, before we had this blue filter, so it's kind of one set of weights W, so W1. We can also have another filter. We can have a W2, which then does this convolution operation over the image, and it produces another activation map. And you can do this, let's say 6 times, so 6 different sets of weights, and then you can obtain 6 different activation maps. So this is kind of the why you would do this. The hope is that one set of weights tells you something about the input image, the other set of weights tells you something else about the input image, and then hopefully if you do this a good amount of times, you get a really good set of values in here that tell you a lot about what's in the input image. So, like I said, because there's this kind of hierarchical structure, it's very similar to, a multi-layer perceptron in that you're taking the output from one layer and passing it into another layer. So, from our 32 by 32 by 3 image, we now have a 28 by 28 by 6 image, and this is now our input into the next convolutional layer. And I actually have a very nice visualization here from the 231N course that I can show you guys that basically shows you what convolution looks like. This is the exact operation. So take a look at this. So here, let me toggle this movement so it doesn't distract over here. I'll just wait for it to finish, and boom. Okay, so we have here filter W, let me make it bigger actually, so you guys can see. All right, so as you can see, we have filter W0 over here, so that's like the first set of weights. We have another filter, W1, and it also shows you the size here. So, this filter here, this first filter, is 3 by 3, but it has depth 3 as well. So that's actually why it's showing you here, there's 3 rows here that show you the different, the depth channel of the weights. And the cool thing is, because you guys are all experts in NumPy now, right? It's actually showing you how you would index to get those values, to get those depth images, to get those depth channels. Now we have the other filter, which is the exact same thing, the exact same size, and then we have our output, which, like I said, it's basically just the output of this, this activation output from doing WX plus B. And that's, what this value is here. So for example, let's look at this case here. So the first thing you'll notice on the input is if this blue is the actual input that we're interested in, something that might look weird is we've introduced this kind of ring of zeros around. And this is called zero padding. Why would we do this? It's simply just to make the filter fit on the image. Because the problem is if you just start with the filter here, so if it covers these 9 squares and then it moves over, there's nothing more to cover over here. It's going to run out of image. And you're not going to get sizes that match. So we do something called zero padding just to make the sizes match. Don't worry about that too much now. But basically, what we're doing here is, okay, so let's actually do the dot product. So all of this row dot with all of this row, 0. This column with this column, it's all 0. So the only thing we care about is 2 times 0 plus, this is another 0, plus 1 times 1, and then 1 times 0. So it's all zeros except for 1. And there must be something else I'm missing. Oh, I guess I've forgotten. There's actually all of these too. So from the first dimension here, we get 0. From this second dimension, or sorry, we get 1 because of these two multiplying each other. From this dimension, we get 1 again, and I think that's it. Oh, did I miss something? Oh, did I go too far down? Yeah, good catch. So sorry, we get just this 1 and a minus 1 over here. So then these two cancel. So then this is all 0. So we still have 1. And then from the very bottom weight, so good eyes on this one, guys. From the very bottom weight, we get these 2 plus these 2, which then gives you 2 up here plus the 1 up here gives you 3. I'm missing something because the output is 4. Thank God that we have plus 1 on the bias. So everything works out. We get 4 on the output, and that's actually how that works. I was sweating a little because I was like, oh man, it's only 3, but we got the bias. So it's all good. So all of that work gave us the 1 value 4 over here. Question over there.
How do you initialize the weights?
Randomly. Usually it's random, but when I say random, I mean this is just like any parametric model, by the way. If you have a linear model like WX plus B, you also will usually initialize that weight matrix to be some Gaussian distribution around 0. Yeah. So that's just, that's a great question. Thank you for asking that. That's exactly the same here in convolutional networks. So all of that to get the 4 over there, but the way that this actually works, like I said, you're sliding this filter over the image. So that you can see how it's basically populating each of those values by doing this, sliding this filter over the image. Cool. So now we understand what convolution is. Oh boy, this is really laggy. All right, so let's go back to here. Okay, so the cool thing, yeah, you have a question?
Is there a physical meaning to these weights?
We're about to look at them. It's a great question, look at this. All right, so yes, there's absolutely a meaning to these weights. And not only that, there's even like I said, we're feeding the output from one layer as the input into another layer. So there's kind of an implicit hierarchy here. Or maybe not implicit, it's pretty explicit, but there's a hierarchy here. So after you train, and I presume these are on ImageNet. So this is a very large data set, 10 million or so images. So after you do this training, on the lowest layer, when I say lowest, I mean the filters that are closest to the image. What those filters have learned, I hope you guys can see this, but do you see these like zebra patterns here? These zebra patterns, when you convolve them over an image, they're actually edge detectors. Why? Because they're subtracting, so let's take this, this is a good example here, this diagonal. So this is like, it's all 1s on the diagonal, and then all negative 1s on either side of the diagonal. So when you convolve this over an image, if you have some part of the image where you have like a diagonal gradient, I don't know, like if I'm standing and then my arm is like this and there's a gradient between my arm and the background, this filter will get a very large number there because it's going to be subtracting exactly this difference between my arm and the background. So this filter is going to have a very high activation value, which is again just this Wx plus b. So this first layer seems to perform some edge detection, and now you can see there's some colorful filters too, because remember they have RGB channels. So you can actually see, not only are we just doing grayscale edge detection, we're also doing color edge detection, which is kind of interesting. The output from these then goes into this set of weights, and if you take a look, this kind of looks like an aggregation of these, where you have this edge detector, but it's not just straight lines. It's not just detecting those specific kinds of edges. It's actually kind of detecting rounded corners or maybe surface characteristics. So it's a little bit of a mid-level feature. It's kind of one step up the hierarchy chain. And then up here, now this is pretty significant. So now here we're like what, 3 layers up from the image. Usually it's actually more, 4, 5, or 6. So we're pretty far away from the image, but because of the way that all of these features are being, fed into each other, and then all of this hierarchy is being imposed, you get some pretty crazy features, some pretty crazy weights coming out here. Like this weight is looking for a honeycomb pattern. This weight is maybe looking for, I don't know, the hubcap of a car or something. You got some circles here. I don't know, some pretty wacky images, but it's actually obtaining some pretty interesting features. All right, so we've talked about convolution. So I said, there's the conv and then there's this pool layer. So this is something else that's going on within a neural network that actually helps us with the computational aspect. So if you remember when we did our convolutional, when we had that nice little sliding picture visualization, the output image was a little bit smaller than the input. If the input was maybe 5 by 5 by 3, the output was maybe 3 by 3 by 6. So in those first 2 dimensions, it's kind of the height and the width. We've shrunk a little bit, but the problem is when you have some of the real data sets that you use for image processing, they're pretty large. So their inputs are like 224 pixels by 224. So the problem is if you keep doing these large convolutions, it's going to be a little bit slow. And also, you're retaining quite a bit of information between layer to layer, where really you want to focus on what's most important. So rather than just keeping all this 224 by 224, what you can do is something called pooling. What is pooling? It's really just fancy name for downsampling. So if you have, some output from some layer that looks like this, and then you want to do something called pooling. Now in this case, there's there's different types of pooling, max, mean, min even. Like there's many different operations you can do, but basically the goal is to select one element from subsets of this activation map, and then output that as the input to the next layer. So for example, here if we're doing max pooling, and we're using, this is kind of something else that you kind of convolve over the image to take certain values away. So rather than doing some dot product here, we're just doing the maximum. So here, if we have like a 2 by 2 filter, and we're convolving it over here, and we're just taking the maximum element. So here it's 6, 8, 3, 4, and look at what we have here, 6, 8, 3, 4. And that's now downsampled our image by 2 times. So, rather than focusing on all of this information, we're just focusing on the kind of the maximally activated activations, or the most important, if I can say, the most important activations from the previous layer. And then all of this output, after all the conv, pooling, nonlinear activation, conv, pooling, nonlinear activation, what we actually get is like a really condensed representation of the image. Because if you remember, I'm not going to go all the way back, but basically, if you remember, we're getting a smaller version of the image, then we're downsampling, and we keep doing this. So we're getting like, from this huge image, we're basically getting almost like a vector that represents this image. And then what we're doing, and we can kind of view this as like some interesting representation of this image in some high dimensional space. What we can do is then treat this vector x as the input to a classifying neural network, or in this case, just a multi-layer perceptron. So you take this, so here your input is just this feature representation from your convolutional layers, and then you can classify with your MLP, and then you get some classification. So when you put it all together, it looks exactly like this. You get a conv, some activation, conv, some activation, pooling, downsizing, again, and then you go through some fully connected layers to get the actual classification output. And when I say actual classification, you're passing in, you have your nonlinear layers and your multi-layer perceptron. At the end, you have some softmax. We talked about that last time. And you get some probabilities at the end. And then these are these probabilities here visualized. That was a lot of words, and my throat actually hurts. So we're going to look at, this is a fantastic visualization of how a neural network is actually working. And all right, this is going to be really cool, I hope. So this is a convolutional neural network. The input, some convolutional layers, some pooling, all that, and then some fully connected stuff out to a classification. This model was trained to recognize handwritten digits. So the data set is called MNIST. Don't worry about the name, but that's its purpose. So let's test this. What if I draw the number 7 over here? Take a look. So this is my input. So actually, the cool thing about this is because it's a 3D visualization, I can take a look at this, at each of these values. So you can see my input in the pixel matrix form, it's this image 7 here. And then what these are showing you is the activation maps from different sets of weights that operated on this input image. So what do you see here, right? You see some edge detected 7s, right? You see some edge detection here, some vertical edge detection, some more edge detection, all of that. And then you see here how we get some kind of this sharp reduction in size. What's going on here? Yell it. Pooling, exactly, max pooling. And you basically then just continue this all up the chain, and then here is our first layer of our multi-layer perceptron at the end. Here's the second layer, and here's our softmax output. So now you know what's hilarious? This model has actually outputted a wrong prediction. I drew a 7, I think it's a 7, and it said I drew a 1 with pretty high confidence. Now, the other great thing about this visualization, which I think is fantastic, is look, you can see what each of the activation maps, what they acted on, what part of the input they acted on. So you see how when I run my mouse over, it shows you what information it took to generate that value. And this is really cool when you look at the fully connected layers, because it really shows you that they truly are fully connected. Every layer, every value here is connected to every value there, and these colors of the lines are the different weight values. So unfortunately it predicted wrong, but what can you do? And then the other cool thing is maybe I can challenge it with like a, and there you go. Oh my God, it predicted an 8. What are you doing? All right, well. So this is a poorly trained neural network, but that's okay. It's still a good example. So that's a fantastic visualization, which I think you guys should play with. All right, so we've talked about, today we've talked about, using convolutional neural networks, which is basically this big neural architecture that is kind of nicely specialized for images, and that we train just using backpropagation with gradient descent. So it's kind of, there's a chain rule, and then with gradient descent and some mini batches, you get some noisy updates and you find some good value of the weights. So this is what we talked about today. What we talked about on Monday was this, using human ingenuity, really trying to engineer what kinds of features you want to get from images, and then put that into some crazy big box here and get some vector, and then classify that using some classifier, some WX plus B or whatever. So the question now is, who wins? What's better? Well, as you might have guessed, since we're actually teaching, since I'm even here teaching you this, yeah, this end-to-end learning approach, this convolutional network, absolutely demolishes. It's ridiculous. So here are some values from, it's a very famous computer vision benchmark test that happens every year. It's called the ILS-VRC ImageNet Large-Scale Visual Recognition Challenge. And this was held in, this specific plot is from 2012. So as you can see, the best human ingenuity errors, so this is showing error, so you want it to go down to 0. So University of Amsterdam, all of their effort, INRIA, Oxford, all of their effort gave them about 25% error, just a little bit more than 25% error. And then, in 2012, and this was really the change, I think this is the pivotal moment in computer vision. There was this group out of my home of University of Toronto, which published a model, a convolutional neural network, and the team was called Supervision, and their error rate was around 15%. So this is now look at this, human ingenuity, hundreds of hours of research, and this is your error reduction. And then this team comes along, absolutely murders your value here. It's ridiculous, right? So this really sparked a huge inrush of effort and research in this field. And since then, I can tell you actually, so AlexNet, the reason it's called AlexNet, the first author, his name is Alex Krzyzewski, maybe you've heard of him. The second author, Ilya Sutskever, maybe you've heard of him, OpenAI, whatever. And then the professor who was authoring this, who was supervising this, Geoff Hinton, maybe you've heard of him. So these three, this was the architecture they came up with. It's pretty simple, like 1, 2, 3, 4, 5, 6, 7 layers. It's pretty simple. But what's funny is back then, and they were also the first group that were using GPU acceleration for CNN. So this is why, training, it's a very computationally intensive process. And these guys, they figured that a GPU is doing this kind of matrix multiplication really quickly. So I remember when they did this, it actually took them 3 weeks to train this on a specialized GPU, really fast, 3 weeks. I think I can now train this model in my desktop GPUs in like 30 minutes. So you can see, right? It really sparked a huge amount of change. And so modern architectures, we went from 7 layers in 2012 to quite a bit in 2014, a pretty ridiculous amount in 2014 from Google, and then a insane amount, this is 150 layers here, this is from Microsoft in 2015, and look at this, right? Now, AlexNet looks like garbage compared to these other architectures, right? And you can see it's showing the amount of layers, but what's funny is, so in 2015, what's really amazing, this error value of 3.57%, this is better than a human. The human's error rate is about 5%. So it's pretty remarkable that actually we get superhuman performance.
Is there some asterisk about the top 5 error versus top 1 error?
Yeah, so top 5 basically just means that, yes, of course, but basically top 1, as you correctly point out, let me just explain this. Top 1 means that your most probably predicted value was the correct class. Top 5 means that in the top 5 of your, if your probability for cat was 50% or 90%, and then your probability for dog was 2.4%, but that was the next highest, if you do this 5 times, you get your top 5 list. And so what this is showing is the classification accuracy, or the error for the class not being in your top 5. Is there a difference? Yes. If you look at top 1, these values will all grow quite a bit. But let me pose it to you. Top 1, yes, it's important for humans. We want to be correct the first time. But who's going to be using models like this? Let's think of Google image search. Top 5 means that image is going to appear in the first row, and you're probably going to click it anyways. So top 5, top 10, even top 25, it's still a very useful metric. Because for the kinds of use cases you want, it actually tells you a lot. So I think actually the reason we're going to zoom in on this Inception v3 architecture is because this is the architecture that you guys are going to use to classify images on your Turtlebots. So there's nothing to explain here. It's a complicated thing. But basically, you can look at what kinds of operations they're doing here and how they're structuring it, and where you get your final output here. All right, so we've walked through quite a bit of material. We walked through kind of talking about this architectures, talking about how you train them, and et cetera. Let's zoom back out and see how you can use them in robotics, which is what you guys are interested in anyways. So one of the most important tasks for robotics is object localization and detection. So a lot of what I was talking about, with classification accuracy is you're given an entire image, and then you want to predict what that image is of. But that's okay, that's kind of useful, but it's pretty useless in a robotics setting because you don't just want to like look at a street scene and say, person. I mean, yes, sure, you're correct, but really the more useful problem is where are these people in the image? Where are the objects in the image? So you can see here that we're trying to find where they are and classify what they are. So this is kind of, you're localizing the object and then detecting what it is. So this is kind of a key problem that we want to focus on in robotics. So the way we can do this with CNNs is instead of only outputting some classification value, you can actually also have a regression aspect where you're trying to predict the 4 numbers that describe the edges of a bounding box. So this pixel here, this pixel here, this pixel here, and this pixel here, and then the classification cat. So that would kind of be a good localization and detection in that image. So this is the way you would phrase, the way that you would do something like this is you would have your output with a class, and then you would have your classification loss, which is, let's say cross entropy. The way that you can regress on the 4 numbers is you can output some 4 numbers, and then have an L2 loss between the actual box around that object. So this is, you're having a regression and a classification component. So the way that you might architect something like this is you have your input image, you have your whole CNN, and then you have your final, this final feature map before you go to fully connected layer, and then you actually take this value and you use it in 2 places. So the first is in the normal way, the classification head, which basically you have some fully connected layers and then some softmax layer, and you have some probabilities for your classes. This other way here, you have the same fully connected layers, but then your output of 4 numbers is actually something that's regressed on, so you use L2. So it's kind of, you have a 2-headed convolutional neural network here, and you can see what that looks like here. Now, the other way that we can do something like this is, rather than just outputting 4 numbers and taking an entire image in, is you can actually just take a fixed size network input. Because remember, in convolutional neural networks, all of your weights, all of your pooling, every operation in there is specialized to a certain input image size, which is usually what your training data set image size is. But if you want to use this on, in the real world where images can be any size, how can you get them to act on these image sizes? Well, what you can do is you can do sliding window. So if you take the network input here, you can feed this top left corner of the image and get a classification score for that. So this is specifically, you would get like quite a matrix for each of the classes, but here we're only looking at the probability for a cat class. So let's say there's like a 0.5 there. You slide the convolution network over to the next section, you get some 0.75, some 0.6 for that bottom left, and then 0.8 for the bottom right. So this is how you can kind of act on a huge image even if you only have a fixed size input. So this approach of having this double-headed network and then also having, some window, like where you actually place this neural network, and then your box, your regression outputs, this entire approach is captured here in this paper, and actually was published here and introduced in this paper in 2014. So it's really combining all of that we talked about to obtain, a final, very accurate prediction of where an object is in an image. So let's try and be a little bit more efficient, because right now, we're kind of sliding things over and we're acting on every single part of the image, even if there might not be anything there. So you can also be prone to false positives, which we want to avoid. So what you can do here is, instead you start by proposing some regions of the image, some regions of interest that you want to then classify further. So basically, rather than scanning the entire image, you're actually just focusing on, 6 or 7 candidate spots, which is, much faster to calculate online. And so basically, you have some proposal method. I guess it doesn't go into it here. You have some proposal method, which could be another neural network, to be honest. And then you just have your same two-headed convolutional neural network to then get a bounding box in those proposed regions. And this is kind of what that process would look like. If you have some large input image, some proposal regions, and then these proposal regions you just treat as images, and then you try and get your classification and bounding box regression there. Now, somewhat recently in 2015, there was now another architecture type, which is even more efficient. It's called YOLO. You only look once, and basically, it's framing detection as regression. So the way that it does this, I don't want to step too much through it, but basically, you divide the image into a fixed size grid cells, and then within each of the grid cells, you're doing this double-headed CNN, and then the outputs of this double-headed CNN, I think you then figure out like what interesting part of the image you should actually look at, and then from those interesting parts, so this is kind of that region proposal, and then from those interesting parts, you then classify again. And this architecture is really fast. You can actually run this on like cell phones. So, the thing that we have to keep in mind, and why we talked about speed and efficiency, is that in robotics, you really need a high-speed performance, right? Because online, if you're moving at, I don't know, I guess for your turtlebots, maybe it's not so important, it's 20 centimeters a second, but if you have a car, and things change pretty fast in 1 second, you really want to have high-speed, the ability to run high-speed classifications. So something like Inception, ResNet, Inception V3, like these huge models, they're really slow to run online, because there's a lot of computations you need to do. So architectures like YOLO and these proposal methods are really fast, and usually they have less weights as well. But you can run these at like 40 frames per second, 20 frames per second, 200 frames per second, with only a small loss. I guess it's a decent loss in performance, but it's really up to you. It's up to you to choose what loss of performance you're looking at. And here there's another architecture called mobile nets. I think the reason they're called mobile is because you can use them in mobile applications. But it's a different type of architecture which was built for speed at a little loss of accuracy. And you can see, how many, this is just basically saying multiplication, addition computations, how many of those you need, and stuff like that. So something else that people have done is, they've basically taken, so with these high-speed convolutional neural networks, what you can do is you can take, oh, I'm surprised it doesn't loop. What you can do is you can take the, you can use a convolutional neural network to directly take some image feed from the front of your car and actually regress, steering commands. And this is actually something that NVIDIA did earlier in like 2005, I think, but also recently in 2016. And here's the architecture they did. And their output is literally just like steering control. It's either steering control and acceleration or just steering control. I forget now. But these are really powerful models which can encode quite a bit of information. And it allows them to reason, even at a high level, about stuff like vehicle control in a driving setting. So this last bit I'll spend on talking about, okay, so we've talked about all these models at length, and we've talked about how you use them and how fast they can be and all that. So the real question is, how do you actually use them? How do you actually get access to and run these programmatically on your robots? So there's a lot of software packages that have that do the kinds of automatic differentiation, gradient computations that we want for training and for inference. And I've listed some of them here. Back in the good old days of 2012, 13, 14, this set of 3 tools, Caffe, Torch, and Theano, they were very popular. Actually, they were the most popular because these guys didn't exist. And these were used all over the place, for vision, for language, you name it. Then, I forget when, I don't know, 2015, TensorFlow came out, and because it was backed by Google and they had this really good software framework and really good software engineering effort put into it, it basically became the predominantly used framework in research and even in application because it's very fast. So that's kind of the first heavyweight. Then PyTorch was released sometime last year, maybe the year before. This is kind of something that's run by Facebook, and it's another big heavyweight, especially in research, because it's really easy to work with. And then there's some others, like MXNet Chain or whatever, which are better at some things for specific applications, but it's really only if you want to be good at some specific application. So, for the most part, you don't have to worry too much. But the whole idea of these kinds of frameworks is that you're specifying an abstract computation graph, remember from the tutorial, where, basically the computation graph in this sense is basically just inputs and outputs of neural network equations. And then the software basically handles the rest for you, which is why they're so popular. So this is actually a visualization of a convolutional neural network architecture in TensorFlow, because you can actually visualize the graph. And so, as you can imagine, there's a lot of chain rule that's kind of going on behind the scenes to do this graph, to do this gradient updates, and to do the weight updates that you care about. And then there's a lot of matrix multiplication to do that forward propagation that you guys care about. So unfortunately, a lot of stuff was left out. The entirety of, like 90% of machine learning we didn't talk about. How you actually pragmatically handle overfitting and how you choose the regularization parameters. How do you even choose some values about tuning? How do you train your model? And then some other things about, just different types of neural network architectures, and even how you can use these kinds of architectures just outside of a purely computer vision standpoint. So here's some courses if you guys are interested. Like I said, a lot of the slide material that we took from today, like if you're interested in computer vision, is directly from the 231N course notes. It's a fantastic course. I highly encourage it. If you want a bit more rigorous fundamentals in machine learning itself, like the stuff we talked about last lecture, 229 and even 216, those are like those are going to be your bread and butter. If you want to learn about recurrent architectures, language, natural language, how we deal with that, this is a great course. And then this is some higher level computer vision course. You read some papers and you learn about really the state of the art. And really there's many more. I mean, half the CS department deals with machine learning. So you can find a lot of information there. So that's all I had in store for today. Hope you guys have a great rest of the week, and come up if you have any questions. Thanks. My throat is dying, oh my God. And I still have to talk for 40 minutes in Michael's group now.
Yeah, so what are we going to talk about?
It's exactly just the IROS work. The idea of using graphs as the kind of the fundamental unit.
Real quick, what's up? The slides that were posted were from last year potential.
Or are they missing?
There's like missing some slides, a little outdated.
Okay, okay. Oh, sorry about that. Okay. We'll definitely look at updating that today.
They're just like small things, like PyTorch weren't there because it wasn't popular.
We'll definitely look at that, yeah.
I had a quick question. What happens if you get if your neural network develops a weight that you get